Hello. This this is a quick lesson on how to use a spreadsheet to calculate the Simpson's rule approximation for an integral and how to use the trapezoid rule to approximate an integral. So first of all, let's I'm not sure what's going on here, but let's go to this. And just to remind you what Simpson's rule is, we want to approximate this integral a to b of f of x dx. Now, the trapezoid rule, which I've hastily written in pen, what you do is you are going to be estimating the integral by trapezoids, and I'm assuming that you've already been introduced to the formula, but just to review, the formula will be have the coefficient, the difference, the width of the interval of integration, that's b minus a, divided by 2 times the number of subintervals you're using. And remember, what you're doing is you're approximating the graph of f by straight line segments, and then you're calculating the area of the trapezoid that the straight line segments and the edges of the interval form. So there is a trapezoid rule formula. For Simpson's, the coefficient in front of all the sums is b minus a over 3n, where n is considered even. And the pattern, the coefficients for the values of the functions go 1, 4, 2, 1, 4, 2, etc., where the f evaluated at a partition point with an odd index gets a 4, and f evaluated at a partition point with an even index gets a 2. And remember, what you're doing is you're approximating this the graph by a best fit parabola using 3 points. Now notice, if your textbook has a different coefficient here, that it's common to say delta x, the width of the interval that you're going to use, is b minus a over the number of points n. So you might see delta x over 2 here, and you might see delta x over 3 there in your textbook. Okay, now let's get on with the actual approximation. Now, the first column, if you just have a small table of data where you only have a few points like we do here, and you only have a few function values at each point, you don't really need this first column here. But let's go ahead but in case you say you have a few hundred, it may be tedious to come up with these coefficients here. But let's go ahead and get to work. Now let's look at the trapezoid approximation. Remember, what you're going to do is you're going to, when you put this into the trapezoidal sum, you're going to be taking these f's. This is f evaluated at your various points. Now, this will be your x values or your input values. These will be your function values at the various endpoints. Now, remember, what the trapezoid rule does is the first thing it does is it takes a sum of the function evaluated at these points times the coefficient, with the first one getting a 1, the last one getting a 1, and all the middle ones getting 2. So I'll just go ahead and call this trap sum right here. So just put that there, or you can call it whatever you like. And then use this thing here, the function space, to multiply C2, that's the function there, times E2. And then you're going to do this for every value of x. So just hit Control C to copy, and then scroll this down, and it does the multiplication automatically for you. Now just pick another thing. I'm going to call this a trap sum. And what I'm going to do there is I'm going to take the sum of, in this case of, okay, this is F2, that's this one here. And you go all the way down to, in this case, F18. So if you notice, this will sum all of these automatically. Now, in this particular case, and there is only, in this case, 16 sums to take. Now, because now we want to find the trapezoid approximation, so you can label it anything you like. And remember, that's going to be B minus A. So B is going to be the furthest X value. So it's going to be, in this case, B18 minus B2 here, divided by, in this case, 2 times, and you want the number of subintervals, and that we can see there's 16 of them. So 2 times 16. Now I'm going to go ahead and put this in greater parentheses here. So this part that I just did is this B minus A over 2n right here. Okay? That's all that is. Now I want to multiply that by all this stuff from this bracket to this bracket. Okay? Well, I've already added that up here, so that's going to be in cell L3, L2. And you can see it highlighted there. And that will be your a trapezoid sum approximation for this integral, the integral of this f over this region here. Now let's do the Simpson sums. This will be the sum. Well, I have to actually do that first, so let's do the Simpson sum. The Simpson coefficient, and then the Simpson sum. And that will be the same f that's equal C2 multiplied by H2. And then we just copy all these. So the Simpson sum now will be the sum of I2 to I18. And then get the Simpson's approximation. You just take the Simpson approximation there. All you do is you take what you have there, your L6, then you multiply that by B minus A, which in this case would be B18 minus B2, start and finish, divided by 3 times the number of subintervals, which we see right here to be 16. And that gives you your Simpson's approximation, which you see is fairly close to the trapezoid approximation. Now, in this particular case, just for example, what I was actually integrating the sine of x between x equals 0 and x equals 4. Well, from the fundamental theorem of calculus, we realize the actual answer is going to be cosine. And since the antiderivative of sine is negative cosine, this is really going to be cosine of 0 minus cosine of 4. So let me, I'm being sloppy here. So let's just label this exact. And I know this is a spreadsheet approximation, but it's going to be 1, that's cosine of 0, minus cosine of 4. And we can see that's the exact number. And we see Simpson's is extraordinarily accurate. Trapezoid's pretty accurate, but a little bit off. So, and that's how you use a spreadsheet to calculate these trapezoid and Simpson's approximations. Thanks for watching.